Okay, so in this video we will solve a kinematics problem that is related to rigid bodies, but in particular it is related to the rotational kinematics of a rigid body. And so to be specific, we are going to be solving a problem which involves finding the angular momentum of a rigid body. So the setup of the problem is as follows. So there is a horizontal axis which bends like this, and so imagine that this was a horizontal rod, but it has been now bent to form this this shape, and at the center of this rod, which by the way is still aligned with the straight portions, there is a disc and this disc is allowed to spin about this axis. So it is mounted perpendicular to this bent part of the rod, and it is given that this rod itself is spinning about this horizontal part, which at an angular speed of omega 1. This is a constant angular speed, and while that is happening, the disk itself is spinning it is spinning like this at an angular speed, constant angular speed of omega 2. The bend of this rod is by an angle beta from the horizontal, and the center point is C. The disk has a mass of m and a radius of r, small r. And so this is the setup of the problem, and the question that we ask is determine the angular momentum of disk about C. Okay, so that's the setup of this problem. So a couple of things here. This is a kinematics problem because just like linear momentum, which involves mass and velocity, this is angular momentum, which again involves mass and angular velocities, and in certain cases velocities as well, and because angular momentum deals with calculation of velocities, it is calculation of angular momentum comes under the kinematics part of rigid bodies. However, rigid bodies are distinct from particles in the sense that particles can only have linear momentum, whereas rigid bodies can have both linear as well as angular momentum. Also, the angular momentum calculations of rigid bodies involve a few more details, and that is why it is important to go over the techniques of deriving angular momentum for rigid bodies, just to make sure that the concepts are clear when we do these derivations. One other unique thing about angular momentum as opposed to, for example, linear momentum is that angular momentum always has to be specified about a point of reference, and typically that point of reference is a fixed point or it can be the center of mass of the rigid body. You cannot arbitrarily say that find the angular momentum of a rigid body. You have to say that find the angular momentum about so and so point, which can be either a fixed point or the center of mass. So here our interest is in finding the angular momentum about the point C, which is the center of mass of this disk. Now the other thing that I just wanted to mention before we started working on this problem is that I would rather like to go over some of the preliminary details as we solve this problem, and so this particular video may not contain the entire angular momentum solution, but rather it may contain one part of it where we clarify the choice of axis and how the preliminary calculations are done to make sure that the problem is well set up. And so we may have to use a second video to go over the entire angular momentum calculation that is asked in this problem. Now, firstly, let us give the basic definition of the angular momentum of a rigid body. So let's say I'm talking about the angular momentum. The angular momentum, if I consider I, j, and k, x, y, and z axis, or a triad, then the angular momentum is going to be h of xi plus h of y j plus h of z k, right? So that is the so that basically says that the angular momentum is a vector, and depending on the choice of triad, it's going to have 3 components. Now, how do we find the angular momentum? Well, the basic formulation of angular momentum is you can express this in the form of a matrix multiplication. So let's say that you have hx, hy, hz, the 3 mutually perpendicular components. Then this is equal to the moment of inertia matrix, so which is Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, and Izz times the angular velocity of the rigid body about the x, y, and z axis. Okay, so this is essentially the h. This is our moment of inertia matrix, and this is the angular velocity. Okay, and when we carry out this multiplication and we express it in terms of the vector, what we get is the following. We get that h of x, so the h of x showing up over here, and it is also that h of x is being calculated through this matrix multiplication. So it is Ixx omega x plus Ixy omega y plus Ixz omega z. And oh, by the way, we should keep in mind that Ixy is equal to Iyx, Ixz is equal to Izx, and Izy is equal to Iyz. Okay, this is just some of the properties of the moment of inertia matrix of any rigid body. Essentially, the moment of inertia matrix is symmetric, and we also know that Ixx, Iyy, and Izz are positive numbers. So hx takes this form, hy is similarly Iy yx omega x plus I yy omega y plus I yz omega z, and similarly hz is equal to, just see if the focus is good, yeah, hz is equal to I zx omega x plus I zy omega y plus I zz omega z. So these are the three components, expressions of the three components along the xyz axis. Now this is true for any xyz axis that we have chosen, but the point of interest, or the point about which the angular momentum is calculated, should be either a fixed point or the center of mass. That's typically what it is done. Okay, so typically the reference point about which the angular momentum is calculated is a fixed point or the center of mass. Now if you consider this problem, okay, if we were to calculate the moment of inertia of, or rather the angular momentum of this disk about an arbitrary fixed point, let's say a fixed point over here or any other place, what happens is that from an arbitrary point of reference, when you calculate these moment of inertias, you can calculate them, but it will be a full matrix in the sense that you will have all these different components. And another thing that happens is that if this is an arbitrary point, as the rigid body rotates, then all of these moment of inertia entries in the matrix can change over time. So that causes some complications when you go to find the rate of change of angular momentum. And keep in mind that the rate of change of angular momentum is indeed a pretty important quantity, because it is instrumental in giving us the rotational equation of motion of a rigid body. So because the rate of change of angular momentum is such an important quantity, we typically try to avoid scenarios where the moment of inertia matrix is going to be a full matrix and where the entries themselves can change over time. It would be really good if the moment of inertia matrix was a constant, okay, so that at least that part would not change as the overall angular momentum changes. So so one thing that we do is we typically, when we find the angular momentum of a rigid body, we typically choose a xyz that is fixed to the rigid body itself. Okay, and what that means is that as the rigid body is turning, these axes are also turning. So imagine that there is a disk that is tumbling and rotating in space. What you have done is, on the disk you have attached with glue a stick representing x-axis, another stick representing y-axis, and another stick representing z-axis. So you have formed these three axes and you have glued them onto one point on the disk, so that as the disk turns, these three axes also turn with it. So it's rigidly attached. So in that case, what happens is that when these three xyz axes are rigidly attached to the rigid body, then the benefit that we get is that the moment of inertia quantities in the matrix, they don't change over time, because as the rigid body turns, the axis also turns, right? So with respect to the axis, it does not see any change in the moment of inertia calculated in the x, y, and z, and neither does it see any change in the product of inertia terms ixy, iyz, and ixz. And that's good, because then you can take when you take the rate of change of angular momentum, you don't have to differentiate the moment of inertia quantities. So that's good. But what is even better is if you can identify what are called the principal axis of the rigid body. The principal axis of the rigid body are, you can consider them to be, in many cases they are, at least one of them is aligned with an axis of symmetry. In many cases all the axes are aligned along an axis of symmetry. In some cases one of the axes will be aligned along the axis of symmetry. Essentially the principal axis is a set of XYZ axes where the moment of inertia reaches extremum values, either maximum or minimum along certain axes. Now if you choose your XYZ as the principal axis fixed to the rigid body, and for the sake of simplicity you can consider this principal axis to be the axis of symmetry, then what happens is that not only does the moment of inertia matrix become constant because the axis is still attached rigidly to the rigid body, but it turns out that because of the symmetry of the axis, or the symmetry with which the axis is located, or the symmetry about that axis of that rigid body, the product of inertia terms becomes 0. Okay, so we make 2 points over here, and that is when XYZ is fixed to rigid body, I is a constant matrix. So all the entries of I are constant. And so when we differentiate the angular momentum to get the rate of change, all we have to do is differentiate the angular velocities, and if the axes are turning, which evidently will be the case because we are considering axes that are fixed to the rigid body, then those unit vectors have to be differentiated. The other case is when XYZ is fixed to rigid body and along principal axis. Okay, so I would just put along axis or axis of symmetry. If this is the case, then I becomes constant plus diagonal. Okay, since IXY equals IYZ equals IZX becomes equal to 0. Okay, and so we always strive when we solve problems on rigid body rotations, we always strive to choose our axis when we are expressing the angular momentum to be fixed to the rigid body along the principal axis. And also perhaps I should clarify here that the origin of that coordinate frame is at the center of mass. Okay, so if we do that, then we have this benefit of I becoming a constant matrix plus a diagonal matrix, so no non-diagonal entries. So in this problem also we are going to take the same approach. We are going to find the angular momentum of this disk about the point C, and we will express it along ijk, where ijk are a triad that is fixed to this rigid body whose origin is at C, and where I, j and k are along the principal axis. So in this case, basically what we want to do is we want to, if you take a front view of this disk where it looks just like a circle, then what we want to do is we want to have the x, y, z to be fixed to this disk, and so it turns with the disk. And you can see that the x-axis is an axis of symmetry, y-axis is an axis of symmetry, and z is also an axis of symmetry. So indeed, this combination x, y, z fixed to the disk form the principal axis, and here it is quite easy to prove that Ixx is equal to 1/4 mr squared, Iyy is also 1/4 mr squared, and Izz is half mr squared. Okay, and so the moment of inertia matrix in this case becomes 1/4 mr squared 0 0 0 1/4 mr squared 0 and 0 0 half mr squared. So you can see that it is constant plus diagonal. Right? So and when this happens, you can then see, going back to our angular momentum expression in this previous page, you can see that when all these product of inertia terms become 0, then hx becomes just Ixx times omega x, hy becomes simply Iyy omega y, and hz becomes simply Izz omega z. So essentially our angular momentum then is going to be equal to 1/4 mr squared omega xi plus 1/4 mr squared omega yj plus half mr squared omega zk, where I, j and k are the unit vectors along this body fixed x, y and z. Okay, so I is essentially this way, j is this way, and k is pointing upwards. Right? Now we still have to determine the angular velocities omega x, omega y and omega z, and that is where we have to be a little careful in resolving these different vectors. Now keep in mind, before we do the calculations, what this omega x, omega y and omega z, what are they actually representative of? They represent, so omega x represents, in the context of this problem, let's say my x-axis, which is fixed to the disk, is let's say that the x-axis that I fix to this disk is at an arbitrary instant. It is like this, right? Let's say that the y-axis at that instant also fixed to this point is like that, and the z-axis is in this direction. This makes sure that your body fixed xyz are along the axis of symmetry, and you can see that indeed this orientation of x, y and z matches with this orientation. So we have said that x and y are along the disk but mutually perpendicular, and z is perpendicular to the disk, and that is exactly how we have drawn this x, y and z. So what is important here is that the angular velocity of this disk needs to be calculated in the x direction, in the y direction and in the z direction. So at an arbitrary instant we need to find out what is the angular velocity of this rigid body, which is, by the way, composed of two rotations. You see, there is one rotation about this horizontal axis, and there is another rotation about the axis of the disk itself. So we need to resolve this overall angular velocity, which is the sum of these two, and resolve them along this x-axis, this y-axis and this z-axis. So we will proceed with that, but in order to do that calculation, we will take a pretty methodical approach, and we will set up some orientation variables that we will use, and we will show how these angular velocity vectors, this one and this one actually turns out to be quite trivial, but this one can be systematically resolved along this x, y and z body fixed frame about the center. So we will show that. Now in order to show that, what we will do is we will consider we will break down this arbitrary orientation of this disk into three separate rotations, okay, and we will show how three separate rotations will produce this arbitrary orientation of this rigid body. These three separate rotations happen by three different angles, and these angles are commonly referred to as Euler angles. You could also call them orientation angles, and essentially the idea is that an arbitrary orientation of a rigid body, and by orientation we mean a rotation. So let's take a rigid body and let's say it's arbitrarily rotated about its center of mass in the three-dimensional space. We can show that any arbitrary orientation of a rigid body can be considered to be composed of three separate rotations. So a rotation by a certain axis, followed by a rotation about a second axis, and that is followed by a rotation about a third axis, and at the end of those three rotations you get this particular orientation, this particular arbitrary orientation. And you can then show that any arbitrary orientation of a rigid body can be arrived at by rotating the rigid body by different angles about those three axes. Okay, so we will show how that type of rotation is applicable over here. And so that is going to be our next step. Let us consider this disk, and actually let me go to a separate page just so that alright, so let us first consider the case where the disk is simply on a horizontal axis. Right, so let's say the disk is just like this, and this is, so right now this is the fixed z-axis, this is the fixed, or this is the inertial z-axis, this is the inertial x-axis, and this is the inertial y-axis. Okay, for the sake of clarity, let us also assume that there is a point P, and the reason we are identifying a point P is because it will help us illustrate how the orientation of this disk changes. So we argue that this particular orientation can be obtained by taking a disk which is aligned this way first, and then first rotating this disk about this z-axis, followed by rotating that rotated configuration about the new y-axis, and then finally rotating that new configuration about the new z-axis. Okay, so let's say that we first turn the disk by an angle alpha. Okay, and so if that is done, then the point P will move here, and this will be my x prime, this will be my y prime. Okay, and so y would have turned by alpha, and x would also have turned by alpha, and z prime would remain where z is. Okay. Furthermore, let's say that the original inertial x-axis, which is the x, y, and z, their unit vectors are capital K here because it's the z-axis, capital I, and capital J. So we will use these unit vectors later on. Right, so this is capital K, this is capital I, and this is capital J unit vectors. So this is the first rotation, and we have rotated by an angle alpha. Then what we do is that we take this axis, we take this disk, and we turn this disk about the new y prime axis, the new y-axis, in the negative y prime direction. So if you did that, what would happen is the following. You would essentially take this axis of symmetry, and you would have turned this axis of symmetry by an angle. That is what would have happened. So so let's say that this was your x prime, this was your y prime, and that is z prime. Now what you have done is you have turned about the y-axis but in the negative y prime direction. So your x prime goes over here and becomes x double prime, and z prime turns and becomes z double prime. And the new orientation well, let me just do one change. Okay, let me just do one change. One of the challenges of teaching rigid body kinematics or rigid body dynamics is that often you want to have a diagram which is kind of representative, and sometimes it's hard to draw it properly. So in this case, I feel that the x-axis that I have drawn should be a little bit more tilted to give you a better idea of how the disk is going to be oriented. In fact, I'll also this x double prime, so that let's say x double prime is here. Okay, so what we have done is we have essentially turned by an angle beta. So now keep in mind that the convention is that if you turn about the axis in the positive direction, that angle is considered to be a positive angle, and if you turn opposite to the axis, that angle is considered a negative angle. So in this case, we will consider that the turn has been of negative beta. Okay, so just trying to get the diagram to be in a decent shape. So now let's say that the disk is like this. You see, so it is a little bit tilted, okay, because of the fact that you have turned about the y-axis or y prime axis. So y double prime remains the same as y prime, and you have turned by an angle beta, and z prime also turned by an angle beta, because your turn is about the z-axis. About the y-axis. So essentially what we are now saying is that the axis of the disk has now been bent. So you can see that we are gradually going towards this configuration. First, what we said is, let's say that we take the normal disk and we turn it, then we twist the axis. So that is the bend, or rather, twist the axis from this horizontal. So from this horizontal, you twist this axis by an angle beta. And lastly, what we do is we give a rotation to this disk about this z double prime axis, but in the negative z double prime direction. So let us sketch that as well. These are a little bit difficult to sketch, but we'll try. So the axis is now tilted by an angle beta. And by the way, the point P which was, this is a little bit exaggeration, so point P which was over here has now gone over here. So P has now traversed to this point. It looks a little bit odd because you see P moved here, but this one looks a little bit too far down. It's just because of the way I sketched it. So this is just hand sketch, so please bear with these diagrams. Then what we do is so this is how the disk is right now. And what we now do is we give a rotation about this axis. And let's say we rotate by an angle theta. We are deliberately rotating in the negative z direction because we want to align these rotations with the angular velocities here. So the first rotation you see was about the positive z-axis to align with this angular velocity. The second rotation was about the negative y direction, and which was done to align with this tilt in the beta direction. By the angle beta. And then we are giving this rotation in the negative z-axis to align with this angular velocity omega 2. So what will happen is P was over here, and if you turn, and so x double prime was here, and y double prime was here, and now we turn about by an angle theta, so we go x triple prime is here. This is our z double prime direction, and it remains the same direction after the turn because the turn is about the z-axis, and y now goes over here, so we now have y triple prime. And so now the disk looks tilted, so now the disk is like that. P has gone to this point, and this angle is theta, and so is this angle. Okay, and so if I call this 1, if I call this 2, and if I call this 3, then 1 is about the z-axis, rotation about z-axis, and it is by an angle alpha. 2 is about y prime axis, which is the new body fixed y-axis of the disk, and it is by an angle negative beta. And 3 is about the z double prime axis, which is the newest body fixed z-axis, and it is by an angle of negative theta. I should put negative theta here. One thing that you will see is that we started off with XYZ, body fixed XYZ, and in the first rotation we rotated the disk about the body fixed Z axis. The second rotation was done about the body fixed Y axis, and the third rotation was also done with respect to the body fixed Z axis. Okay, so this is this is basically called a ZYZ set of rotations, and it is one way to define Euler angles. And here our Euler angles are alpha, beta, theta. These are our Euler angles. You can also call them orientation angles. Okay, so one thing that we see is that therefore a sequence of rotations in Z, Y, Z by alpha, beta, theta in that order, orients the rigid body in an arbitrary orientation. So an arbitrary orientation of this rigid body can always be obtained by a sequence of these rotations. So first with respect to the body fixed Z, then with respect to the body fixed Y, and then with respect to the body fixed Z axis, the new body fixed Z axis again. And once we do this sequence of rotations, then by proper angles, then we can always take your original disk, which is initially oriented like this, to an arbitrary orientation. And so this is the set of orientations that we are going to use to help us determine how these angular velocities are going to be expressed in this body fixed XYZ. So another thing to note here is that body fixed XYZ started from capital XYZ orientation in 1, so in diagram 1, and ended with X triple prime, Y triple prime, Z triple prime orientation after 3. So it shows how the body fixed XYZ axis changed its orientation. So first it went from capital XYZ to X prime, Y prime, Z prime. That was the first rotation. After the second rotation, it went from X prime, Y prime, Z prime to X double prime, Y double prime, Z double prime. And after the third rotation, it went from X double prime, Y double prime, Z double prime to X triple prime, Y triple prime, Z triple prime. Okay, so this now associated with each of these rotations, we can come up with a matrix that shows how an initial a vector that is represented in the initial capital X, capital Y, capital Z, which is aligned with the inertial XYZ frame, how it can be represented in an X prime, Y prime, Z prime. Then by using this rotation, we can show how a vector that is expressed in X prime, Y prime, Z prime can be expressed in X double prime, Y double prime, Z double prime. And similarly, we can show how a vector that is represented in X double prime, Y double prime, Z double prime can be expressed in X triple prime, Y triple prime, z triple prime using this rotation. And so we will show that. Let me just see where my notes are with respect to that. Yes. All right. So okay, so if we go back to this original diagram, you will see that there are two angular velocities. One is in the horizontal direction, and one is along the axis of symmetry of the disk itself. So if I want to, so what we want to do, remember, we want to express omega 1 and omega 2 in terms of angular velocities we want to express omega 1 and omega 2 in terms of omega x, omega y and omega z, where omega x, omega y, omega z are oriented along the body fixed x, y and z. So how do we do that rotation? Well, we first note that omega 1, the vector omega 1, is nothing but 0 in the I direction plus 0 in the j direction plus omega 1 in the k direction. And this capital Ijk corresponds to the starting ijk unit vectors. Remember that the omega 1 angular velocity is consistent with alpha. So this was the angular velocity omega 1. Okay, so omega 1 is indeed in the capital K direction. Okay, however, this is not good enough because we want to express it in terms of the I, j and k which are body fixed. So we want to transform this to x prime, x triple prime, y triple prime, z triple prime axis. Okay. On the other hand, the angular velocity omega 2 is already in the negative k direction. Omega 2 is already in the negative k direction. So this is already in x triple prime, y triple prime, z triple prime axis. So we don't need to do any transformation of omega 2, because if you recall, this is the direction of omega 2. Omega 2 is in the direction of minus theta. So indeed the angular velocity omega 2 is in the z prime direction. It's just negative z prime, and that's why we are using small ij and k for x triple prime, y triple prime, z triple prime. So we should just mention that x triple prime will be represented by I, y triple prime will be represented by small j, and z triple prime will be represented by small k. Okay. So now the question is, how do we express this vector? Is already done. How do we express omega 1? Right. So here we use what are called rotation matrices, and the general idea is that if I take a vector which is in the original coordinates system x, y, z, capital X, Y, Z, which in our case was the inertial frame, and we understand that we have first rotated by an angle alpha. So rotation by an angle alpha, and this rotation was in the z-axis, body fixed z. So there is a matrix, and we will show what this matrix is. And then there is a rotation that was done by an angle negative beta, and this was about the y-axis. And finally there was a rotation that we did about negative theta, and it was of the amount of negative theta about the new body fixed z-axis. So this is z, y, z in the opposite sequence, you see, and this then will give us the vector in x triple prime, y triple prime, z triple prime axis. Okay, so this is the these are called the rotation matrices. And these rotation matrices help us to do this transformation from a vector that is represented in your original set of axes that you started off with, okay, in the new set of axes, which in this case are the body fixed axis to the disk after the 3 rotations were done, and it will be a structured way of finding the vector representation. So we will stop here. We have already discussed this for about an hour or so. You can see that these problems take quite a bit of time if you want to take a very structured approach to solve them, and I'm trying to explain all the steps. I'm trying my best. One challenge that we have here with rigid body mechanics or kinematics is just the visualization. Hopefully by solving many problems, the visual aspect, orientational aspects will become a little bit clearer as you grasp the techniques for solving kinematics of rigid bodies. In the next video, what we'll do is we'll start from here, and we will complete the angular momentum calculation that we started for this problem, and then there are some other parts of this same problem that we'll tackle in later discussions. So that's it for now. Thank you.